Hi guys, so this is going to be the second video on magnetism, and we're going to talk a little bit about magnetic fields and currents being carried by wires and solenoids and rectangular coils and things like that. So let's put a title, which is always good: magnetic fields. Okay. The first thing that I would like to mention about magnetic fields is that you can produce them. They can be produced by electric currents. So an electric current can produce one. And in the last video we saw how that can happen, and you just have electrons going in this direction inside of a wire, which by convention means, by the way, that the current is going in that direction, and we mentioned that also in the last video, that the current is regarded as the positive flow of charge and the electrons are negative. So if these guys are going in that direction, then current's going like that. And when we do our right thumb rule, we have to put our thumb along the direction of the current. So current is going to the left in this case, and your thumb would go like that, and your right hand, so your fingers would wrap around like that, where this is in front of the cable and that's behind of the cable there. So this would be in front, and you would produce this magnetic field. And just to make sure that that diagram makes sense, the red part is the part of the back of the cable, and the yellow part is the part in the front. So yeah, current would be going like that, and the magnetic field would be going around in that direction. And so this is important to know, that the electric currents can produce magnetic fields. So hopefully you know that. And so a lot of electrical appliances use these. The fact that magnetic fields are created by electric currents. So if you start an electric current, you do it in a certain way, you can start a magnetic field, and that can induce magnetism in a material, and you can use all sorts of effects in circuits to produce to kickstart different circuits and get machines moving, or to get them just started, and all kinds of stuff. So we'll talk about those things a little bit more later. So what's a magnetic field? So a good definition for a magnetic field that you can write down if you want now is a magnetic field. So I'm going to write it here. A magnetic. So feel free to take notes on any of this. I know some of you have taken notes already, but hopefully this will be useful anyway. A magnetic field is a region where magnetic materials like iron and steel and so magnetic materials and current carrying wires will experience a force. So a magnetic field is a region of space where magnetic materials and current carrying wires will experience a force. So not only a current carrying wire will produce a magnetic field, but also if you have a magnetic field and you put a current carrying wire inside of the field, then it will feel a force. It will go one way or another. So the currents and magnetic fields are related very intimately. The relationship goes in both directions. Now remember that this is done using the right hand rule. We had a picture of it in the previous video, and your left hand rule we'll use for a different thing. We'll talk about that a bit later. So to know what the direction the magnetic field lines go when you have a current carrying wire, you use your right hand. And for something else I will talk about later, you use your left hand. So now that we know this about magnetic fields around wires, you can imagine almost somebody coming up with this idea and saying, well, if I now know that if I have it's a very bad line, if I know that if I have a wire and the current is going in this direction, I can create a field around it that would go like that. Then let's do something clever with the wire. Let's bend it like that. This would continue the circuit down here. This would continue the circuit down there. And now look what happens. Magnetic field lines on this line, on this side, would go out of the screen and into the screen. And here the same, out of the screen and into the screen. And there would be the one circle, and there would be a bigger circle around it also. Bigger circle around it at that same bigger diameter, but at the same point in the cable, and a bigger circle and a bigger circle. There would be concentric circles like that around the wire, and here it's going down. So if you put your right hand down, you'll see that you put your right thumb downwards, you'll see that they go into the screen here. That goes into the screen, and that comes out of the screen. And there's another concentric circle like that going into the screen, and here goes out, and here the same. So if you imagine these growing and growing and growing, when they get here into the middle, they would both be going into the screen. So if you look at it them from the back, like the back of an arrow, the lines would be going like this into the screen, like that. Yeah, so they're all going like that in, and it goes in, and they're going in the same direction. So you can amplify the they're going into the screen, by the way. It's a bit hard to draw, but hopefully you can see what I mean. So you can amplify the effect of magnetic field. You can make a magnetic field much bigger by having what's called a rectangular coil. So this is a rectangular coil. So a way of saying this is you can say that the circular magnetic field around the sides, they make each other stronger, so they reinforce each other's here at the center, right, of these two currents. And if you imagine doing this but with loads of individual wires, so each the coil has lots of turns, so it just goes around and around and around. It's got lots of different wires. Then the magnetic field of each individual wire will add up like that, and you'll create a really, really strong magnetic field in the middle. So creating coils with lots of wires is a great way to create powerful magnets. And since these magnets are caused by electric currents, well, we'll talk a bit more about the detail of electromagnets later, but anyway, hopefully that makes sense so far. So that was a rectangular coil. Now let's think about something called solenoid. So we'll make this one in orange. Don't know why. Solenoid. Solenoid. It's just called like that. And solenoid is kind of a coiled wire, like in a spiral. So the way you, I'll stick with blue for wires. I don't know why I chose blue today, but if you imagine a wire coming in like that, and then going around, and then coming back up here, and then coming around, and coming back up here, and something like that, and then coming out here somewhere, and here was coming in the current was coming in this direction, and here the current's coming out. If you imagine that, then now let's see how we're gonna draw this. We've been doing green for the field lines, so let's keep the green, and Well, let's think about what would happen here with the magnetic field. If there's a current going in that direction, if you put your thumb along that direction and your fingers would coil like that, right? So there would be a field coming, kind of coming out from here. Like that. And another one here, or there, for example. And then if you do the same thing here, where the wire, the current's here coming up, then you can see that your fingers would also wrap around in this direction, and so into the screen it would kind of go like that, so they would be coming from kind of like that from outside and into the coil inside, and then outside around here. But if you do this, they all reinforce each other, and instead of getting the current coming out around here somewhere, it just keeps on going, keeps on going, keeps on going, keeps on going, and the fields reinforce each other, and you get these really strong magnetic field inside, like that, and it's going inside of the wire. And then on the outside it just behaves like a normal magnet, so your lines would do a closed loop like that, and these would do a closed loop also, but they're a bit too big to draw, but they would go like that, and this would go like that, and like that, and this would come around like that, and if we did another one here, come around like that. So you create a really strong, these are coming from completing the loops of these two, and like that. So you create a very strong magnetic field, and the characteristics of this in a solenoid are that the magnetic field inside of the solenoid is a strong field, and it's uniform. Uniform means that the space between these lines is the same between this one and this one, and then between this one and this one, and between this one and this one. So you create a uniform strong magnetic field, which can be very, very useful for a lot of things. A solenoid is a very clever and useful thing. Another thing to know is that outside of the solenoid itself, it behaves like a normal bar magnet. So the lines, field lines, would look very much the same as if this was one magnet, and therefore, well, let's say that first. So it behaves outside. It behaves the same way as a bar magnet, right? And third thing to know is that well, if it behaves the same as a bar magnet, then you can imagine that one of the sides is going to be a north and one of the sides is going to be a south pole. So it behaves very much like that. So it has its ends behave as north and south poles, and I'll tell you how to identify which one is which in a second. Poles. And a fourth thing to know about the solenoid is that if you change the direction of the current, which is pretty easy, you can just connect your whatever's powering this the other way around, or you can even have an alternating current source where the direction is changing all the time. But if you change the direction of the current, then the north and south poles switch, right? Hopefully that's intuitive to you. North and south poles switch, or they swap. They swap ends, they swap sides. We don't have very much time left, but if you're looking at it from the behind, from here, for example, look, the current's going like that. So it will be going like this, up and then down, and this creates a north. Let me see. No, that's rubbish. It would create a south, because the S looks like that, and you always remember it by the shape. The other one would create a north. If it's going like that, then you would have a north where you have it like that. Hopefully that makes sense.